Problem number 5 gives us an aircraft flying at a speed of 500 miles per hour and an elevation of 10 miles above Earth, beginning at the North Pole, so up here, and flying south along Greenwich meridians of this direction. And it gives also a spy satellite orbiting the Earth at an elevation 4,800 miles above Earth in a circular orbit in the same plane as the Greenwich meridian, so also this way. Miraculously, the plane and satellite always lie on the same radial line, so essentially they're always going to be in the same line like this from the center of the Earth. Assume that the radius of the Earth is 3,960 miles. Part A wants us to find when is the plane directly over a location with latitude 74 degrees, 30 minutes, 18 seconds north for the first time. So in order to figure out this problem, first we have to know something about latitudes, and that's that Earth is divided into 180 degrees, 90 degrees in each direction. So you have 0 here, 90 degrees plus this way, and then minus 90 degrees this way. And that we also need to know that 30 minutes is 1/60th of a degree, and 18 seconds is 1/60th of a minute. So what we need to do now is convert 74 degrees, 30 minutes, 18 seconds into a usable angle that we can use. So here's a little bit better diagram. I have the pivot point being here, Earth's radius 3,960, the plane being 10 nautical miles away from Earth, and the satellite being 4,800 miles away from Earth. So here we have the 74 degrees, 30 minutes, 18 seconds. What I did was created an addition table where I started out with 74 degrees, and then I converted 30 minutes into degrees. And since we said there's 60 minutes per degree, we just do 30 over 60, and that gives you 1/2. Next, we need to convert 18 seconds. We know that 18 seconds or 1 second is 1/60th of a minute, so 18 seconds is 18/60ths of a minute, and we know that each minute is 1/60th of a degree. So if we just multiply that out, then you get 0.005 degrees, and you add 74, 1/2, and 0.005 to get 74.505. The problem with this is that what it's going to give you is 74.5 degrees from the 0, which 0 is here, so 74 is going to be up this way. So we need to find this angle, which is going to be 90 degrees minus the 74 and change that we just found. So we do 90 minus 74.505, and that leaves us with 15.495 degrees, which is the angle that we're going to be using for the remainder of this problem. So the first thing that it asks us to do is, okay, so we need to figure out when, so that's time, the plane is directly over a location with latitude 74 degrees, 30 minutes, 18 seconds north. So what that's going to mean is what time is it going to be from, is the plane going to be right here, because this is when it's going to be over 74 degrees. So I set up a diagram here where this is our plane, this is the arc or the path that it's covering, this is the radius from here to the center of the Earth, which is our pivot point, and here's the angle that it's traveling along. So we know that the distance of the arc is some portion of a circumference. In this case, the circumference is going to be, the circle that they are circumnavigating is going to have a radius of 3,970. We get that by doing 3,960 plus 10 miles above Earth to get a radius of 3,970. Then we know that 15.495 is just some portion of 360. So we do 15.495 divided by 360 and multiply that by the circumference of the Earth, which is, of course, is 2 pi r, or pi d, which gives us a distance of 1,073.64 miles. but it's not asking us how far he's traveling. It's asking us when he'll be right here. So we have to use the information given that the plane is traveling at 500 miles per hour. So we take our distance equals rate times time formula, plug in our distance of 1073.64, use our rate of 500 miles per hour, multiply that times time, solve for time, and we get 2.15 hours, or 2 hours and 9 minutes. Next, we need to figure out how fast the satellite is moving. So the information that we need to solve that is already given to us as well, and we solve for it. So essentially what we're doing is finding out the distance of this arc, and knowing that the satellite stays in line with the plane, we know that it will reach right here at time 2.15 hours. And so what we do is do our 15.495 divided by 360 to get our portion of the arc, multiply that by the circumference of the arc, or 2 pi d, using 8,760 as the radius, or 2 pi r, excuse me, or pi d. This time we used 8,760 because we did the distance the satellite is from the Earth plus radius of the Earth. For d, we get 2,369.04 miles. And we know that the plane got there in 2.15 hours, so should we, which means that the satellite is traveling its distance at 1,101.9 miles per hour. Next, the problem asks us when is the plane directly over the equator and how far has it traveled, and part D, how far has the satellite traveled when the plane is directly over the equator. So we're essentially doing the same thing we did up here, except instead of using angle 15.495, we're using angle 90. Why? Because the equator, of course, is at angle 0, and the difference in angles between 0 and 90 is going to be 90. So we set up our diagram here. We use the same radii that we used before, 3970 and 8760 respectively, and then solve for d. This time, instead of doing 15 point something over 360, we just do 90 over 360, or we can just understand that 90 is 1/4 of a circle, and multiply that by the circumference, and what you get is distance equals 6,236.06 miles. Again, it's asking us when the plane's going to be over the equator. So we take that distance, set it equal to 500 miles per hour times time, and you get 12.47 hours, or about 12 hours and 28 minutes. Do the same thing for the satellite, except now using radius 8760. So we get 1/4 times 2 pi times 8760, and we get distance is 13,760.18 miles, which I believe is what the question was asking for. How far has the satellite traveled? There it is. All right, that's it. Thanks.